Let's finish off our physics before Christmas break by talking a little bit about waves at boundaries. You guys saw in the demonstrations we just did a minute ago that when a wave goes from one medium to another, when it encounters a boundary between one material and another, you will always get some reflection and you will always get some transmission. In other words, some of it will always bounce back and some of it will keep going. Now, how much keeps going and how much reflects depends upon how different the materials are. If they're very, very similar, then you will get mostly transmission. If the materials are very different, then you're going to get mostly reflection. In the two demonstrations that we did just a few minutes ago, the two materials in both cases were very, very different from one another. We had a wave going from slinky to person. Therefore, most of the wave was reflected. Only a little bit was transmitted to the person. In the second demonstration, the wave went from slinky to air, which again are very different. So most of the wave was reflected and only a little bit was transmitted. Let's look at the part of the wave that is reflected. Under certain conditions, the part of the wave that's reflected will be right side up. Other conditions, the part of the wave that's reflected will be upside down. The wave will be reflected, that is the portion that is reflected. Some of it gets transmitted always. Sometimes it's a little bit of the wave, sometimes it's a lot of the wave that gets transmitted. But the portion that gets reflected, whether it's just a little bit or a lot, will be either upside down or right side up. It will be right side up or upright if the wave goes from a medium that is less dense to more dense. How do you remember that? Well, in the classroom, we saw that the wave was reflected upside down. Less dense to more dense. This is that's backwards actually. Should be from more dense to less dense. Yeah, it should be more dense to less dense. Sorry, backwards. When we were in the atrium, it went from slinky to air, and when it went from slinky to air, it was reflected on the same side. Right, I sent it down on the library side, it came back on the library side. When it went from more dense to less dense, it was reflected right side up. Now, it's reflected upside down when the wave goes from less dense to more dense. In the classroom, the wave went from slinky to person. The person was more dense than the slinky was, therefore the wave was reflected upside down. Now, another way to think of this, generally, when you're going from more dense to less dense, the slinky or whatever it is not attached. And it's going to be reflected right side up when it's not attached, when it's going from more dense to less dense. And when it is going from less dense to more dense, generally speaking, the mediums are attached, like when the slinky is being held by a person. So in the first case, more dense to less dense, slinky to air, the slinky was just resting in the air. When we're going from less dense to more dense, the slinky was attached to the person, and it was reflected upside down. How do you think the amplitude of the reflected wave will compare to the amplitude of the wave that struck the boundary? Remember what amplitude is related to. How do you think the amplitude of the wave that is reflected will compare to the amplitude of the wave that we had in the first place, Nick? It's going to be less, sometimes a little bit less, sometimes it's a lot less, right? If most of the wave is reflected, then the amplitude will be just a little bit less because you only lost a little bit of energy going to the new medium. But if most of the wave is transmitted, then you only have a little bit of the wave reflected. You only have, therefore, a little bit of energy reflected, and therefore the amplitude of the reflected wave is going to be very small compared to the original wave. Now, this one I can't demonstrate. I wish I could. It's called the law of reflection. The reason I can't demonstrate it is because it's a two-dimensional thing. Here's a boundary. You guys have all played pool before, right? Like billiards pool. You hit a pool ball off of the bumper like this, strikes the bumper right here. Where does it go? It goes down this way, right? Same thing happens with waves. When a wave encounters a boundary at an angle that we'll call theta I, that's the angle of incidence. What's that green line? What do you think that green line is called? In physics, we have a word for anything that is 90 degrees. Something that is 90 degrees or perpendicular, you've heard this word before, and you've heard it in that context where it's been perpendicular as well. What is it? Normal. Yeah, this is what we call a normal line, because this line is perpendicular to the boundary. The angle of incidence as measured from the normal line will be equal to the angle of reflection as measured from the normal line. Theta I equals theta R. That's the law of reflection. You guys have had an intuitive notion of this. I know you have. I know you do. Okay, when you're playing pool, you know which angle, roughly at least, which angle that pool ball is going to come off the bumper with, right? You know that the angle of incidence equals the angle of reflection. Well, the same thing happens with waves. It's just a little bit harder to demonstrate with waves in a slinky than it is with a pool ball. Finally, let's take a look at the part of the wave that's transmitted, that keeps going. We're not going to look at right side up, upside down, and so on, because the part of the wave that's transmitted will always be right side up. It's never going to be transmitted upside down. But let's take a look at a couple variables. What changes when we go into the new medium? Well, I'm going to tell you that the speed changes, the speed of the wave. The speed will either speed up or slow down. Now, Bruce just said the energy changes. Yeah, it actually does, because some of the wave is going to be reflected, so you're going to lose a little bit of energy in that process, right? So the energy changes as well, although that's not what I want to focus on here, okay? The speed changes. Now, as a result of the speed changing, the wavelength will also change. So if it increases in speed, and it can, the wave can go to a faster speed. If it does, the wavelength will get bigger. If the speed decreases, in other words, if the wave slows down, then the wavelength will get smaller. Those are the two variables that will change. What variable do you think stays the same when we go into the new medium? Frequency stays the same, because once the wave has been made, the frequency doesn't change. Now, I'm going to go back here to the first one again and put in brackets 1. What's that? Theta. The reason I'm going to put that in brackets, the direction, is because the direction sometimes changes. Okay, the speed will always change in the new medium. The wavelength will always change. The frequency will always stay the same. The direction will sometimes change. If you're going from medium A to medium B, and you're going straight on like this, the speed will change, the wavelength will change, but the direction won't. The direction will stay the same. But if you're going like this, from medium A to medium B, the speed will change, the wavelength will change, and the direction will also change. So it's in brackets because it sometimes changes, but not always. Perfect timing. Have a great night. Have a great weekend. Have a great Christmas, everyone, and a great New Year's. And we'll see you guys next year.